CubeSats are headed to deep space. In 2018, history was made by JPL with the success of the MARCO Mars Cube 1 missions. Later this year, in 2021, NASA will make history again with the launch of 13 interplanetary CubeSats on the Artemis 1 mission. My name is Ben Malphrus from Morehead State, and I'm the PI on one of those missions, Lunar IceCube. I'm happy to be here today at the CubeSat Developers Workshop, and my focus will be to describe the assembly, integration, and testing processes associated with preparing the Lunar IceCube mission for launch. The Lunar IceCube mission is a collaboration between Morehead State University's Space Science Center, the NASA Goddard Space Flight Center, the NASA Jet Propulsion Laboratory, the NASA Independent Verification and Validation Center, and the Busek Space Propulsion Company. Lunar IceCube is both a science mission and a technology demonstration mission. The primary science goal is to prospect for water ice and other volatiles on the lunar surface using an infrared spectrometer developed by NASA Goddard. The innovative spectrometer is known as BIRCHES, the Broadband Infrared Compact High-Resolution Exploration Spectrometer. The basic idea is to tune BIRCHES to a variety of water ice lines between 3 and 5 microns and map the distribution of water over the course of a lunar day cycle and with respect to lunar topography. The hope is that these observations will lend insight into the transport physics of water ice across the lunar surface. Water tends to collect in permanently shadowed regions, PSRs, at the extreme lunar latitudes, particularly in the south polar regions of the moon. Water is created or deposited at a variety of latitudes, including mid-latitudes, and it's not really well understood how water is transported from these mid-latitudes to the PSRs. It's hoped that these observations will lend insight into the underlying transport physics. As a tech demonstrator, Lunar IceCube will demonstrate enabling technologies for the exploration of the solar system with small satellites. Among these are an innovative electric propulsion system, an RF ion engine developed by the Busek company referred to as the BIT-3. The BIT-3 uses solid-state iodine, which has a high energy density as the propellant, and generates a significant delta V of approximately 1.3 kilometers per second. This engine, combined with the use of the Interplanetary Superhighway using low-energy manifold trajectories, allows the mission to achieve near rectilinear halo orbit and then the science orbit, ultimately, with extremely low use of propellant. Additional enabling technologies include a full X-band ranging transponder developed by JPL, the IRIS version 2.1 transponder, a full integrated star tracker and attitude determination and control system developed by Blue Canyon Technologies, the XACT, and a custom high-power solar array and associated EPS system developed by Pumpkin Incorporated with Morehead State University. The team is preparing for flight readiness review at the end of May and for launch in November. The mission duration is approximately 2 years and includes a long outbound trajectory phase and an approximately 2-month or 2 lunar day cycle science mission. The current status of the mission is in NASA Mission Phase D. The spacecraft has been built and is in testing. The BIRCHES instrument is undergoing calibration and characterization at the NASA Goddard Space Flight Center. All of the ground data systems are currently being tested. Each DSN station that is utilized for ground support is being tested with the ground data systems. The Lunar IceCube concept of operations, or CONOPS, is somewhat complicated. We get a ride to Earth escape with the SLS launch vehicle and utilize the RF ion engine to undertake a couple of deterministic maneuvers to put us in an appropriate dynamic state for the lunar flyby, which occurs at about 5.5 days after deployment. After the lunar flyby, we use the low-thrust propulsion system to nudge us into a circuitous route that takes us on an Earth flyby and takes us 1,000,000+ kilometers away from the Earth. Then we fall back to the Earth-Moon system in the right dynamic state to undergo a loosely bound capture. From a chaotic lunar capture, we transition into a near rectilinear halo orbit, at which point we can decide the perfect time to dive into the science orbit. The science orbit is a highly elliptical orbit that takes us to 100 kilometers paraloon and approximately 7,000 kilometers apoloon above the lunar surface. Once we achieve the lunar science orbit, we use the infrared spectrometer to map targets on the lunar surface for approximately 1 lunar day cycle or 1 Earth month. An extended mission hopefully will extend a couple of additional months. There's enough propellant to maintain the lunar science orbit for at least 2, possibly 3 months. After the science mission is complete, the disposition plan involves impacting the lunar surface on the far side of the moon. This type mission, with a low-thrust propulsion system carrying approximately 1.3 kilograms of propellant, is only possible through the use of an innovation developed at the Jet Propulsion Laboratory by Martin Lowe and colleagues called the Interplanetary Superhighway. The Interplanetary Superhighway uses low-energy manifold trajectories based on stable and unstable manifolds and ballistic capture. Manifolds are created by Lagrange points through in-body effects and can be modeled for the first time now realistically using interplanetary trajectory models. The challenge with the manifold trajectories is that they never actually go exactly where you want to go. That's why you have to hop from one to another, hence the term manifold trajectories. In the case of Lunar IceCube, it turns out to be a circuitous route that takes us about 1.5 million kilometers away from the Earth-Moon system, but still gets us to the moon with an extraordinarily low amount of delta V. The Interplanetary Superhighway is an extraordinary innovation that makes exploration of the solar system with small satellites possible. It will no doubt open the door for deep space exploration with CubeSats. The Lunar IceCube mission takes advantage of the Interplanetary Superhighway by using a complex transfer trajectory designed for low-thrust propulsion systems. It uses minimum delta V, but the disadvantage is that it takes about 270 days for the entire trajectory. The trajectory brings the spacecraft back to the moon in the right dynamic state that allows the moon's gravity to capture the spacecraft in a weakly stable lunar orbit. The propulsion system can then be used to sequentially lower the apoapsis to spiral the spacecraft down into a final science orbit. That process takes 80 to 90 days, so the entire trajectory, with the outbound trajectory about 170, 180 days, and spiral down phase about 80 to 90 days, is approximately 270 days in total. To track and range and command the spacecraft and to pull down data and telemetry requires the use of the Deep Space Network and a complex ground data system. The complexity of the ground data system is one aspect of an interplanetary CubeSat mission that the Lunar IceCube team significantly underestimated. However, there are a number of tools developed by the Jet Propulsion Laboratory and other NASA centers that make the development of an appropriate ground data system much more feasible for small teams. These tools include the Advanced Multi-Mission Operations System, or AMOS, and the AMOS Instrument Toolkit, AIT. They also include spacecraft planning and analysis tools and a variety of other tools. Even though the tools are available, they do require modification and significant testing to incorporate them into your ground data system. The Phase D activities that I would like to focus on are associated with Assembly, Integration, and Testing, AI&T. AI&T can be broken down into several different categories: Assembly, Integration, and Functional Testing, Space Environment Testing, Ground Data Systems Testing, and Flight Readiness Testing. Assembly, integration, and functional testing takes place after critical design review and after some form of integration readiness review. FlatSat development and testing can continue in parallel, but assembly, integration, and testing involves the flight hardware. The build of the flight hardware generally involves several steps, from dry build to flight build, often known as the wet build, with a variety of different aspects of functional testing interspersed in between. Abbreviated functional testing, comprehensive functional testing, comprehensive performance testing, all are associated with various aspects of the build. It's sort of a build and test cycle generally as you go. Toward the end of the functional testing cycle, more sophisticated tests are undertaken. Day-in-the-life testing, mission modes testing, end-to-end testing, and some form of RF compatibility testing with the ground stations that are to be used. Space environmental testing is dictated by the Launch Services Program and/or for mission assurance. These typically include vibration testing, thermal testing, cold soak, hot soak at extreme temperatures, EM-1, thermal vacuum testing, and often thermal vacuum power management testing. Ground data systems testing can take a variety of different forms. Typically for interplanetary space missions that are using the Deep Space Network, a number of different aspects are involved, ranging from simulation file creation to actually testing with each front end of the Deep Space Network. These tests involve Spacelink extension bind and what are known as GDS tests, essentially communication tests over the network between the mission MOC and the antenna site with every DSN antenna that is to be used. The final round of pre-launch testing is flight readiness testing. Flight readiness testing involves operational readiness testing and mission services training activities. Flight readiness testing reflects day-in-the-life operations of the space mission, the spacecraft and the payload. Often, anomaly and exception handling is introduced into flight readiness training. Flight readiness testing involves all personnel that are central to spacecraft operations. It involves the mission operations specialists, the payload specialists, the ground station and ground network personnel. Flight readiness testing is a key aspect of mission operation assurance. Shown here is the Lunar IceCube vehicle build and test flow diagram. It is not meant to be prescriptive as a test flow diagram for all interplanetary smallsat missions, but rather shown as an example of how flight build and testing is interspersed as a process. The next series of slides illustrates the sequential processes associated with AI&T. Flatsat evolution starts with very simple systems, maybe a few of the subsystems, and evolves in complexity as subsystems are brought online. Flatsat test environments are excellent software development platforms. They also serve to facilitate working out the communication protocol between subsystems. Ultimately, the Flatsat should represent all of the subsystems, or at least emulators or simulators of the primary subsystems. Shown here are images that represent the evolution of the Lunar IceCube electrical and mechanical systems. We've often found that it's useful to incorporate 3D printed models before subsystems are available. These help with fit checks and mechanical orientation. AI&T is often an iterative process. Subsystems are put together, built, tested, deintegrated, rebuilt, retested, and ultimately come together as a functional system. Environmental and performance testing are very interesting and also often iterative. Assembly testing and calibration of the ground support equipment involved in testing, or the GSE, is also very interesting and can be underestimated in terms of the time that's required. For me, one of the most important and interesting tests is end-to-end testing. End-to-end testing involves the spacecraft at some level, could be the Flatsat, could be the flight hardware. It involves the ground station, it involves the Mission Operations Center, and it can involve the network over which the data and commands are passed. End-to-end testing, if it can be accomplished, can be key to mission assurance. In conclusion, AI&T is the process where the rubber meets the road in spacecraft engineering. AI&T is often an iterative process with build and test cycles interspersed. Testing should generally evolve from simple functional testing to more comprehensive testing and culminate in test-like-you-fly activities. Extensive functional and performance testing we have found is key to mission success. Interplanetary missions, owing to the extreme thermal and radiation environments, require extensive testing and anomaly mitigation processes. Preparing for launch, as we found with the Lunar IceCube mission, is an exciting process and always a learning experience. And there always seems to be less time toward the end. We are really looking forward to the launch of Artemis 1 in November of 2021. Thank you very much for your time and attention.